What's up, guys? This is Sammy here to give you another rousing stats lecture today. Today we're going to be going over Lab 2, sampling and probability, but first I wanted to go over some general housekeeping things. Going forward, instead of emailing your assignments, your homework assignments and your lab assignments to us, to Paul and I, please upload them onto Blackboard. There are folders for the appropriate lab and homeworks. And you might not see all of them, but they will be there when you need to upload. So like for example, Lab 2 and Homework 2 are up there right now. Lab 2 is going to be due tonight at 11:59. I know there were some technical difficulties last week with R, so I just wanted to give everybody some time, and I didn't want there to be any pressure. Like the whole point of this lab is to learn, so sometimes it's hard to do that under time pressure, especially if you're not familiar with the concepts. Going into point two, these videos are going to be kind of like we're going to put these videos out before the lab sessions, but they're meant to be used as a supplement during lab and after lab as well. It's really nice when you have something to refer to, like this video, but it's also nice when you have somebody to ask questions to in person. So my aim with recording this video is while we're in lab, you guys, whoever wants to use this video, can use this video, should use this video, and as questions arise, please feel free to ask. Because then I'll be able to kind of like walk around and hopefully get to everybody before class is over. And I know class goes a little bit late, but please feel free to ask questions. I'll stay a little bit after class if need be. And then also, oh, and I should add, like, these lab videos will essentially be giving you answers on your labs, but keep in mind that you will be taking an exam pretty soon, and you won't be able to watch videos for these exams, like during the exam. So just make sure you understand the concepts and yeah, ask questions. And then the third point is take a literal screenshot of your R syntax and output when a lab or homework question asks for it. And the reason being is um, if anyone needs help with anything, it's easier for us to help if we know what you typed in and what came out, for one. And two, we kind of want to prevent people from just typing in um, syntax that they see on other people's pages, other people's assignments as well. So make sure to just take a literal screenshot of your syntax and the output when the lab and the homework asks for it. Okay, z-scores and normal distributions. So there are a couple formulas that you need to know in order to calculate either a z-score of a data point or the raw score of the data point. And we have, I wonder if I can use this cursor tool here. Ooh. Okay, so we have a very poorly drawn circle around the formula you need to calculate the z-score, and then pretty simple, the raw score formula for a population. And remember, we're working generally with populations right now, but we're going to be getting into samples, especially towards the end of this lab. So the first question is asking, three people have the following scores on test one. We're given the mean of the scores, and we're given the standard deviation of those scores. What are their z-scores? So the first person has a z-score, or excuse me, a raw score of 45. And in order to convert that into a z-score, we just need to use the formula to calculate it or to um, turn it into a z-score. So their z-score is going to be -1. Person two, similar kind of deal. You can see their score is the 50, so the x on the in the numerator part of that fraction, x is their score, so that's 50. The other 50 is from the mean, and then it's being divided by 5 because that's the standard deviation. And we get a z-score of 0. And then similar thing for the third person. And now we have a z-score of 1. So we're going to do the opposite here. We're going to be converting raw scores into z-scores. And with some basic algebra, we can take the z-score that we already know, -1, and then multiply that by sigma, or the standard deviation of the population, and then plus mu, which is the population mean, and that's 50, and we get 45, and then similar thing, 50 for the second one, and then the same equation here, because again, we are trying to get the raw scores. So question 3. This is I think this question really puts z-scores into perspective. Like you have the SAT and you have the ACT, and they're not out of the same amount of points, but you need to standardize them in order to see how in order to even be able to compare these scores. So for the SAT scores, we're going to be converting the raw score into a z-score. And if you haven't noticed by now, the equations for z-scores and raw scores, or the formula rather, are in the upper right-hand corner. And when we calculate the z-score for the SAT scores, we get 0.29. And then for the ACT scores, we get negative 0.18. And I think 0.29 is a bit bigger than negative 0.18. So the SAT scores are probably the best scores in this set. So now we have a set of questions um, that are going to kind of help us understand what z-scores mean conceptually on a normal distribution. So this answer is asking you to draw the normal distribution curve, or this question is asking you to draw the normal distribution curve. Make sure you're indicating your answers on the distribution curve, in addition to giving your answer through the equations that you use to reach that answer. But we're given the population mean, and then we're given the standard deviation of the population, which is 15. And then we're asked, what is the proportion of people that have an IQ score of 115 or above? So if we have the raw score, we need to figure out the z-score. That's 115 minus 100, which is the population mean, divided by the standard deviation of the population, and then we get 1. But what do we do with that? Well, first things first, look at the distribution on the bottom. The standard deviation of the IQ scores is equal to 15. So in the center of that poorly drawn distribution, we have a population mean of 100, and one standard deviation up, we have 115. So you're literally adding the standard deviation of the population is 15. You're adding 15 to 100, and then you get 115, and that's plus 1 standard deviations above the mean. And then 130 is 2 standard deviations above the mean. And then the same thing for the other side. So 85 is 1 standard deviation below the mean, and then 70 is 2 standard deviations below the mean. So again, the standard deviation of the IQ scores is equal to 15. This is kind of a good way to think about it. Like we're just like by sectioning it off there, because we're looking for the proportion of people who have an IQ score of 115 or above. Now we can't get exact numbers looking at that distribution, so we're going to go to our handy dandy z-table, and we are going to find the z-value that we calculated from step 1 on our z-chart. So that's the proportion between the mean and z, meaning 15.87% of people had a score of 115 or above. So like think about it conceptually, just like by seeing what we did, what number we got, the proportion from the z table, the z chart, and how that translates to this distribution here in relation to this question, because it's asking above 115. Now, it's going to get a little bit trickier here, but bear with me. Essentially the same kind of steps though, right? 130 or below the mean. We still need to calculate the z-score because we're going to use the table. And we're looking for the proportion of people who have an IQ of 130 or below. So that. And if we have the z-score, well, clearly we need to go to the z-table, and the proportion that's associated with that z-score is 0.0228. But like, look at that shaded area. Does that look like like 2.28%? It isn't. So we're going to need to take the whole distribution. It's 100, right? So 1 minus 0.0228 equals 0.9772, meaning that 97.72% of people had a score of 130 or lower. I really encourage you when you're taking an exam or like for any of these questions, if you're struggling, try to draw a distribution even if it's not asking you to, because it really does help conceptualize this stuff and like ingrain it. This question is a little bit different, but again, kind of same template. So we're given two scores and we're asked what proportion of people fall within those two scores, sets of scores. So again, calculate the z-score for 85. We get -1. And then we have to do the same thing for 115, and then we get +1. And then going to our distribution, that's what we're looking for. And notice it's one standard deviation above, exactly one standard deviation above, and exactly one standard deviation below. Now, in theory, you could just say it's 72% or whatever, but that would be wrong. So we need to go to our handy dandy z table. We need to find the associated proportion with with the z-score of 1. So that's 0.1587. And that's the z-score that's associated with the standard deviation of +1 and the standard deviation of -1. So again, we're asked what proportion of people fall in between the IQ scores of 85 and 115. So we need to subtract those z-scores from the entire proportion, or from the entire distribution. Framed as a proportion or percentage, whichever you prefer. We take 1, and then we just subtract 0.1587 twice from 1, and we're left with 0.6826, which equates to 68.26% of people who had an IQ score between 85 and 115. And again, I just look at this conceptually. Like if you would have said 72, it would have been wrong. So you really need to use that z-table to your advantage to get exact statistics. All right, question 5. Suppose the people living in a particular city had a mean score of 40 and a standard deviation of 5 on a measure of concern about the environment. Assume that these concern scores are normally distributed. Again, we're working with normal distributions. What's the minimum score a person has to have in order to be in the top 10% 10th percentile. So we know the percentile, obviously. We're not given a z-score or a raw score, but knowing the percentile should help us in finding that relevant z-score. So once again, we will need to go to our handy dandy table and find the top 10th percentile to locate the z-score, which I've already given you, unfortunately. And how did I get a score of 1.28? Well, we have these two proportions there in that on the right hand side of the screen in that red oval, and we have 0.1003, and then we also have 0.0985. If we're looking at if we're trying to find the score that's closest to 0.1, which equates to the 10th percentile, we need to find the closest proportion to that, and 0.1003 is much closer to the 10th percentile than 0.0985 is, meaning we will be using this z-score of 1.28, as you can already see. Okay, great. We have the z-score. Now, let's find the raw score. We have all of the other components to find the raw score, and then we get 46.14. So the minimum score a person needs to place in the top 10th percentile is 46.4. And again, I've kind of revised the distribution a little bit. I didn't include the bracket, but I'm sure you guys have the gist of it by now. The population mean is 40, so that it really does make sense that the top, and then like 45 is one standard deviation above the mean, and we know that in between the mean and one standard deviation, 36% of the cases fall underneath that. So it's got to be farther up a little bit, and you can, I guess you can kind of sort of like guess, but you, it's not going to be correct. You really need to try and do it this way. So what I'm trying to say is conceptualize it, and it'll help you understand what these equations are actually doing, as opposed to just like rote memorization. I believe this is the last question, but now we're working with the distribution of sampling means. So we are given the population mean, and we're given the standard deviation of the population. And we are asked to determine the IQ score needed for the top 10% of the IQ distribution. So similar to the last question, however, we're working with a sample size of 60. So this is specific to that sample size of 60 as opposed to the population, which is what we were working with before. So we don't know the standard deviation of the sample, but chances are the standard deviation of the sample is going to be smaller, usually this is the case, than the standard deviation of the population mean, because we're literally taking this sample from the population. So maybe finding the standard error might be helpful in this situation. And we know the equation for standard error. So we get 1.94. And now we know the standard error. We need to go to find the z-score that it's associated with. And unfortunately, I've already given you the answer right there. But similar to the last question, we just have to find the proportion that's closest to 10%. So that would be 1.28, which is how we got that number. And we can begin to calculate the raw score. But again, we only have the standard error of the mean, so we need to include that number in there. And then we get 102.48. So I really encourage you, especially with this question, it might be really helpful to draw a distribution just to conceptually understand it. But to be considered in the top 10th percentile, this sample size of 60 means to have an average IQ score of 102.48. I believe that was the last question. So Yeah, good work, team. I will see you guys in the lab today. Be sure to, I guess, yeah, be sure to just come to lab. There's not much we can do right now. All right, see you guys in a little bit. Bye.